In our final related rate example, we're going to assume that we have an observer standing on the ground, and the observer is watching a plane that happens to be flying in a direction that is away from the observer at a speed of 250 miles per hour and a constant altitude of 4 miles. What we're interested in is when the angle that the observer is looking at the plane relative to the ground is 60 degrees, at what rate is that angle changing? If you imagine as the plane flies overhead, when the observer looks straight up, then as the plane continues to fly away, that angle theta is going to be diminishing. We're going to start essentially at a 90-degree angle when it's directly overhead, and it'll get smaller and smaller the further away that the plane gets. So we're going to expect that d theta dt will be a negative value as a result, and that will be useful to kind of check our answer when we get further into the problem. So looking at what we know here, we know dx dt is going to be 250 miles per hour, and it's going to be positive because x is going to be growing. The plane is going to be getting further away from the observer in this case. We have a value for y, and that's fixed. That's not going to change. And then we need to deal with our theta. So we're going to need to have some kind of a trig function involved here in order to get theta involved. And then when we take the derivative of whatever we have that involves theta, we'll pick up a d theta dt, and that's what we're being asked to find. How fast is theta changing when theta is equal to 60 degrees? That will be d theta dt. So since I know the opposite side of this right triangle, and I know the adjacent side, it might be useful to use the tangent here. So let's write that tangent of theta is going to be equal to the opposite over the adjacent, or 4 over x. We now have a relationship that involves theta and it involves x. When we take a derivative, we're going to get a d theta dt. We're also going to get a dx dt. We know dx dt. We're looking for d theta dt. We know what theta is. We've been told that. We can calculate what x is from the picture that we have here and from the equation we have. We have all the different pieces that we need to get to d theta dt. So let's take a derivative here. Derivative of the tangent of theta is going to be the secant squared of theta, d theta dt. And if I think of 4 over x as 4x to the negative 1, then the derivative of the other side is going to be negative 4 x to the negative 2 dx dt. So if we plug some numbers in here, let's see what we've got. So we have the secant squared of 60 degrees times d theta dt is going to be equal to negative 4 divided by x squared times dx dt, which is 250. So the only thing we don't know is x right now. So let's see if we can use this original equation to come up with x. So what we're going to need to do is figure out what is the tangent of 60 degrees. Well, if you remember from your unit circle, it's the square root of 3. If you don't remember that, it may be useful to remember that the sine of 60 degrees is square root of 3 over 2. The cosine of 60 degrees is 1/2, and the tangent is the quotient of those two things. Square root of 3 over 2 divided by 1 over 2, we'll end up with square root of 3 over 1, or just square root of 3. So square root of 3 is going to be equal to 4 over x. So if we rearrange things a little bit here, we're going to end up with x is equal to 4 divided by the square root of 3. That means that x squared will be equal to 16/3, and that's what we're looking for in our equation here. Now we're also going to need to know what the secant squared of 60 degrees is. Well, secant is 1 over cosine, and we just said that the cosine of 60 degrees is 1/2. So 1 over that would be 2. If we square it, we get 4. So secant squared of 60 degrees is going to be equal to 4. So let's plug in here. We're going to end up with 4 times d theta dt is equal to negative 4 divided by 16/3 times 250. So let's take everything that we have on the two sides here, and then we'll, or everything we have on the right-hand side, excuse me. Let's see if we can get a number for the right-hand side, then we can divide by 4, and that should lead us to a good value for d theta dt. That's going to be in radians, because calculus gives us radians, even though we're evaluating the trig function using degrees. We're still going to end up with radians as units here, because that's what calculus works best with. And we're going to pick up radians per hour because our speed was miles per hour. So if I take -4 and divide it by 16/3, and I'm putting the 16/3 in parentheses to make sure that that works out right, I get -0.75. If I multiply that by 250, I get -187.5. And if I divide that by 4, I get -46.875 radians per hour, which isn't a very useful number. We might be more interested in radians per minute or even radians per second. So if we did that in radians per minute, we would need to divide by 60. That would be -0.78125 radians per minute. Or if we went to radians per second, we would divide by 60 again, and we would end up with -0.013 approximately radians per second. Typically a problem will probably give you a better idea of what kind of units it's looking for, especially if you're doing this on WebAssign. But these are a couple of different ways to go about answering this problem. The last note I want to make is that our d theta dt did end up being negative, and that's exactly what we expected. That's a good sign that we're on the right track here.